and thank you very much to the organisers for organising and for inviting me, and thank you all for coming. I hope you're feeling good after last night. I'm feeling... No, wait, that's not very loud. Right, so the word spectrum is kind of enormously ambiguous, but actually there are fewer meanings of spectrum than you might imagine, in the sense that most of the meanings are somehow related to each other. So, you know, there are the physics and chemistry type meanings. There's spectrum in the sense of emission and absorption. Here's hydrogen here. There's closely related. There's mass spectroscopy, which is a very useful thing. And at the other end of the spectrum, there's there's also various kind of apparently entirely pure mathematical meanings of it. So there's the linear algebra meaning of spectrum as meaning the collection of eigenvalues, which preferably come with their algebraic multiplicities. And then, extremely closely related to that, there's the meaning of spectrum in the sense of functional analysis or in the sense of PDEs. And then, kind of seemingly somewhat away from that, but actually related, is the commutative algebra meaning of spectrum, where the spectrum of a ring, the commutative ring, is a set of prime ideals. So I might come back to that later. And there are various other related meanings, for example, in operator algebras. And there's some kind of, I mean, I'm not going to say very much about the relationships between them, but there are some relationships. On the other hand, there are one or two meanings of spectrum that have, as far as I know, nothing to do with this large family of meanings. So, in particular, homotopy theorists talk about, who use the word spectrum to mean something along the lines of infinite loop space. So that, I think, has got almost nothing to do with the other kinds of spectrum, and then there's this kind of spectrum, and that's got nothing to do with that. So I'm not going to talk about that stuff. So as far as this talk is concerned, I'm just going to talk about something very simple, which is the simplest thing on that list, namely the eigenvalues of a linear operator on a finite-dimensional vector space. And so people had this attitude to linear algebra that is kind of, it's all done and all completely understood, and moreover, all completely understood by you when you were an undergraduate. And I don't think, I mean, I don't know about you personally are brilliant, of course, but some other people, I think, have a slightly overconfident attitude in regard to linear algebra. There are quite a lot of things that I think haven't really settled down yet. So I'm going to use spectrum in this way. I just mean the set, right, so the context is an operator on a finite dimensional vector space, or if you prefer, a square matrix. And I'm just going to use the word spectrum to mean the set of eigenvalues and coming with their algebraic multiplicities. So we'll come back to this. Now, this is kind of, I mean, the spectrum is somehow a difficult animal. For example, if you've got two operators, if you've got S and T operating on the same vector space, if you've got two matrices of the same size, then, and you know the spectrum of S and you know the spectrum of T, but you don't know S and T themselves, then there's almost nothing you can say about the spectrum of the composite or the spectrum of the sum. They certainly, spec S and spec T certainly don't determine the spec of the composite or of the sum. It's easy to give counterexamples, but not only do they fail to determine them, they tell you almost nothing about them. And so, you know, if you were thinking categorically, you might hope that spec of S composed with T was somehow obtained from spec S and spec T, or something like this. And that's just not the case. On the other hand, I mean, in some sense, the spectrum is socially important. When I say socially, I mean kind of, you know, socially in mathematical sciences. It's something that, as the first slide showed, appears everywhere. And so it's undoubtedly an important thing, which means that it should be possible to find some sort of abstract characterization of it, some sort of description of it that is that's nice and clean. And one reason why you might want such a description is if, for example, you want to push the spectrum concept into new contexts. For example, there's been some effort to define a non-commutative spectrum in multiple contexts. I'm not claiming this result that I'm going to show you helps with that, but that is the kind of thing you want to do. And so the one goal of this talk is to give you a nice, clean characterization of the spectrum in a sense. So that's what's going to happen. And the plan is this. I'm going to explain the following theorem. So it says that if you think about invariants of linear operators, just on finite dimensional vector spaces, so things like, trace, determinant, whatever, among all the invariants that have these two properties, that are cyclic and balanced, and I need to explain to you what those words mean, among all those operators, the universal one is almost the spectrum, but not quite the spectrum. The spectrum, just the non-zero spectrum, the non-zero eigenvalues with algebraic multiplicities. So I'm going to explain the theorem, and that's the main part of this talk. So first I'm going to talk about linear algebra done right, and then I'm going to talk about invariants. I'm going to explain those two words in red, and then I'm going to state the theorem. That's the plan. Okay, so we begin with some linear algebra. And this phrase, linear algebra done right, is not mine. There's a quite well-known book by Sheldon Axler here he justifies the provocative title. If you haven't come across this book before, the main selling point of it is that it's a 10-chapter book, and determinants don't appear until chapter 10. So he claims that almost everything is better done without determinants. And I'm not sure whether I agree with the thesis about determinants, but but he does do a great deal of linear algebra in a different way than is usually done, and I think a better way in many cases. Okay, so the core concepts of this book, in my opinion, are the eventual image and the eventual kernel. So let me just fix some notation. We're going to be over an algebraically closed field, and X is always going to be a finite-dimensional vector space over it, and T is going to be a linear map from X to X, a linear operator on X. And so given T, you get this chain of smaller and smaller subspaces like this. And the eventual image is defined to be their intersection. So this thing is smaller than the ordinary image. On the other hand, if you take the kernel of increasing iterates of T, the kernels get bigger and bigger. More and more things get sent to zero as you apply T more and more times. These are kind of dynamical definitions. And the eventual kernel is the union of this chain of subspaces. You get a subspace, and it's larger than the ordinary kernel. And these two concepts are extremely useful. So I'm going to show you two ways in which they're useful, two decompositions of a linear operator. So we have our linear operator T on our vector space X, and it's a fact that X decomposes the direct sum of its eventual kernel and its eventual image, and here T0 is nilpotent, in other words some power of it's 0, and T cross, that's a cross not an X there, T cross is invertible. So just to explain the notation, I'm making two statements here. First of all, that the vector space X decomposes as a direct sum of the eventual kernel and the eventual image. And secondly, that T restricts to those two subspaces. It restricts as a nilpotent operator on the first and an invertible operator on the second. So that's not enormously hard to prove. It's the only way of decomposing T as a nilpotent thing plus an invertible thing. Okay, so that's that. And you can contrast the ordinary kernel and image. So ordinarily, of course, it's not true that that X is the sum of the kernel and the image, let alone the direct sum. Although the dimensions do add up. Right. So that's that, and that's the first way of decomposing an operator. Yeah.
And I'm sorry, I think I've missed something. So what do the arrows, the curly arrows above the letters?
Right, sorry. Yes, that's just a notation for T being an operator on X. It's an arrow from X to X labelled by T.
Right.
It's curled round because the domain and the codomain are the same. Yeah, sorry, I should have said. Any others? Okay, thanks. So the second way of decomposing a linear operator is like this. That it decomposes as a big direct sum of this form. And so here, the operators T lambda, the only eigenvalue of T lambda is lambda, or another way of saying that is that T lambda minus lambda is nilpotent. Of course, when I say minus lambda, I mean minus lambda times the identity. And again, that's saying, first of all, that X is a direct sum of these subspaces, and secondly, that the operators restrict as described. And so this thing here, the eventual kernel of T minus lambda, is ordinarily called the generalized eigenspace of lambda. I prefer to call it the eventual eigenspace of lambda. So it's, the ordinary eigenspaces consist of the vectors which, when you hit them once with T minus lambda, go to 0. The eventual eigenspace consists of the vectors where, when you hit them many times with T minus lambda, they eventually go to 0. So it's bigger than the ordinary eigenspace. And you can contrast the fact that if you're using ordinary eigenspaces, ordinary kernels, then usually this isn't the case. In fact, it's only the case, it's the case exactly when T is diagonalizable. That's more or less the definition. But this is always true for all T.
Is the eigenvalues of T?
Sorry?
Little k, is that the eigenvalues of T?
No, little k is a field we're over.
Oh.
So,
So
this is trivial. It's almost always trivial.
Oh.
There's only finitely many where it's non-trivial, and those are exactly the eigenvalues. Okay. So it's really a finite direct sum. No, it looks like an infinite one.
Is there a way to generalize? So T is an endomap on X.
Yes.
Is there a way to generalize it to maps from X to Y to a different space?
Not that I know. I mean, everything about this is to do with iterating the operator. Yeah. I don't know anything to say about that. The other thing that I didn't write, but I should have, but I'll say out loud, is that this is very, very closely related to Jordan normal form. Jordan normal form is one step further than this. You have to analyse the nilpotents to get from here to Jordan normal form, but almost all the uses of Jordan normal form actually only need this statement. Okay, so those are the two decompositions, and let's just see them again. So that's the first one, and that's the second one, and they're somehow compatible with each other. So first of all, in the second one, you've got something called T lambda, for each scalar lambda, and in particular you've got T0, because 0 is a scalar. And that's the same as this T0 here. Moreover, the second decomposition is a refinement of the first, in the sense that if you remove the 0 summand from here, so you get this right-hand side there, then that is just the eventual image in the first decomposition. Okay. Right, so that's all in linear algebra done, right? One good thing about it is that it gives you a handle on the notion of algebraic multiplicity. So, I mean, the way I learned linear algebra, at least, how is algebraic multiplicity defined? So determinant was defined in some kind of, probably inductively by going along the rows and stuff. And then the characteristic polynomial is defined as the determinant of something or other. And then the algebraic multiplicity is defined as the power that appears in the characteristic polynomial. It's not exactly, intuitive. But this, I think, gives a really good idea of what the meaning of algebraic multiplicity is. So, take a scalar. You can define the algebraic multiplicity as the dimension of the eventual eigenspace. And that's equivalent to the usual definition. I wish it was called dynamic multiplicity, because it's got this dynamical flavour about it. Keep doing the operator. So it says how much of the space is eventually annihilated by T minus lambda. And then because of this second decomposition here, you can take dimensions on both sides, and you see that the sum of the algebraic multiplicities is the dimension of the whole space. Again, all but finitely many of these summands are 0. And you can then make a bunch of definitions that agree with the classical definition. So the trace is the sum of the eigenvalues with multiplicity, the determinant is the product with multiplicity, the characteristic polynomial is given in this way here, and these are all equivalent to the usual definitions, but it's just a different way of framing everything that I think is more conceptual. Okay, so that's all stuff from Axeler's book that I think provides this good point of view. Are there any small questions on that before I move on? Okay. So one thing to point out is that the eventual image construction is functorial. So I'm going to use the following notation. Given any category, you can build a new category whose objects, so the objects of the new category are the endomorphisms in the old category. So again, this notation here means T is a map from X to X in C. So the objects of endo C are the endomorphisms in C. The maps in endo C, so the maps from one endomorphism to the other, are the maps of the underlying objects that make the obvious equation hold. Okay, so they're just the maps that are compatible with the operator. So if you're kind of categorically inclined, then you'll want to think of endo C as being the functor category from the additive monoid of natural numbers seen as a one-object category into C. That's what this is. Anyway, so for our purposes, C is going to be the category of finite-dimensional vector spaces, and so endo of C is in this case the category of linear operators. Its objects are linear operators. Its maps are maps between linear operators. And what I'm saying, alluding to in the title here, functoriality of the eventual image, is that there's a functor that takes an operator, replaces the underlying space with the eventual image, and replaces the operator with its restriction. So this is in fact an automorphism, an invertible endomorphism here. This formula here says how this function is defined on objects, and on maps it's defined by restriction. In other words, if you start with a map of operators, like up here, and then it restricts to a map between their eventual images, that's not terribly hard to see. Okay, so that's something that we're going to need quite soon. Right. So the theorem I flashed up at the beginning said something or other about invariants. So let me say what I mean by invariants. So given any category.
So
yep.
eventual kernel is not functorial, or?
Oh yes, it is. Yes, sorry. Yeah, the eventual image, eventual kernel, ordinary image, ordinary kernel, they're all functorial. But I just wanted to highlight that the eventual images. Yeah. Yeah.
So this composition of S and S is a vector space, right? And F is a map.
Nope. S is. Okay, so maybe I'll write this. You can't see it, but so this. Okay. So that notation means that.
Okay, so it's reversed. What you choose.
I'll write it over here so everyone can see. Thanks, Chris. Right, so S is a map from Y to Y.
And is it an idempotent functor? In the sense that
Yes.
Yeah?
Yes, it is. In fact, right. So this is slightly peripheral to the talk, but you could replace endo by auto here, the category of automorphisms. This functor here is both left and right adjoint to the inclusion. It has two dual universal properties. Wonderfully. So yeah, it's idempotent. Okay. So invariants. I want to talk about invariants of linear operators, but generally, if you have any category E, you can talk about invariants of objects of E. And all I mean by that is just some quantity or something or other that is invariant under isomorphism. So it's a function from the isomorphism classes of objects into some set omega, anything you like. And so we're interested in invariants of linear operators. So for us, E is going to be the category of, well, this category of linear operators. So for example, the trace, in which case you take omega to be the scale, the field of scalars, or the determinants, or the characteristic polynomial, or you could take the algebraic multiplicity of 33, or whatever your favourite scalar. The spectrum is an invariant that takes values in the collection of finite sets with multiplicity of scalars. And also, I'm going to be talking about the invertible spectrum. So the invertible spectrum, and again I'm using this cross symbol here, is defined as the set of non-zero eigenvalues with their algebraic multiplicities. So that's a finite subset of multiplicities of k cross the non-zero scalars. And I'll explain why I'm doing that. A final invariant is the isomorphism type or isomorphism class of this operator here, of the invertible operator associated to T. That's another invariant. Which you can, there's a kind of combinatorial description of those isomorphism classes via Jordan normal form, but I don't need to talk about that. So let me say something about this invertible spectrum. Why is it interesting to think about the non-zero eigenvalues particularly? You might think that the normal spectrum was the more natural thing. Maybe it is. But here's the first observation, that if we know the dimension of the space we're operating on, then knowing one is equivalent to knowing the other. So of course, if you know the spectrum, then you know the invertible spectrum. So you just throw away the multiplicity of 0. But if you know the invertible spectrum, then you know the whole spectrum, because the only thing missing is the multiplicity of 0, which you get by this formula here. Remember, the algebraic multiplicities add up to the dimension of x. So knowing one is equivalent to knowing the other, assuming you know the space you're operating on. Okay, so why are the non-zero eigenvalues interesting? Well, one way of putting it is this. So usually when we talk about eigenvalues, we think about t minus lambda, or t minus lambda I, where I is the identity operator. And you ask whether this thing is singular. But it wouldn't be very different to be asking whether this thing is singular or invertible, putting the scalar over here. But there is a little bit of difference, because you can't divide through by lambda or mu if they're not zero. If they're zero. And so if you think about it for a moment, you'll see that knowing which values of mu this is singular for is exactly knowing what the non-zero spectrum is, the invertible spectrum is. So that's one reason. Another reason is because of cyclicity, and so this is what I have to tell you about next. Okay, so cyclic invariance. So I'm going to say that an invariant, right, so we're going to be thinking about endomorphisms in a category, which is usually finite dimensional vector spaces, and invariants of endomorphisms, for example, invariants of linear operators. And I'm going to say that an invariant of endomorphisms is cyclic if it has the same value on G composed with F and F composed with G, whenever those things make sense. And if you have a cyclic invariant, the example that everyone is probably most familiar with is trace. So if you have any two linear maps going in opposite directions, the trace of one composite is equal to the trace of the other. And so the reason for the name is that if you've got a cyclic invariant, then it assigns a value to any diagram like this. So you could write, for example, phi is cyclic, then it makes sense to talk about phi of, say, this fourth cycle here. It doesn't matter where in the cycle you start, it's all the same. Okay, so that's what cyclic means, and the eventual image is a cyclic invariant for the following reason. This is there are no proofs in this talk, and this is the closest that this talk is going to come to a proof, so here we go. If you start out with two maps in opposite directions, then you get two maps in opposite directions in the category of operators. I was sitting here on, maybe it was Tuesday, and everyone was talking about Alice and Bob, and I felt that I didn't fit in, and I had this idea that I should call one of these Alice and one of these Bob. Put little pictures of Alice and Bob like everyone else was doing on Tuesday. But my instincts as a mathematician took over, and I thought, no, they have to be called FG and GF. Anyway, so remember that the eventual image is functorial, so you can apply it throughout to this diagram. And And then this is what you get, right? You apply the eventual image functor and you get this diagram of operators. And maps between, and linear maps. But if you think about the composites of these two maps, one way round or the other. So the composite one way round is, well, it's do f and do g. Right, so you get, so the composite at this end is gf, but this notation is just a restriction of gf. I mean, this f is a restriction of the original f, that g is a restriction of the original g, that gf is a restriction of gf. And so the composite one way round is this, the composite the other way round is that, and both those things are invertible. Because remember, that's where they came from. They're the invertible parts of the operator in the first decomposition. So you've got a pair of maps going in opposite directions, and we don't know that their composites both way rounds are the identity, but we do know that their composites both way rounds are invertible. And that implies that that f and g themselves are invertible. So that means that the two sides here are isomorphic to each other. Right, so it doesn't matter whether you do g first and then f, or f first and then g. And that's saying exactly that if you take the isomorphism type of the eventual image and its associated operator, that's a cyclic invariant. And in fact, you can show it's the universal cyclic invariant, the initial cyclic invariant of linear operators. Okay, so that's
You didn't
that's
say what
eventually
the category of invariance was.
well, so by an invariant, I just mean something that's isomorphism invariant. And we've got a category of linear operators. That's this category here.
Initial cyclic invariance, initial.
I see.
Track of, where which
Right.
category that's initial in.
Okay, so there's a category of invariance. Yeah.
Right,
So
that's what
so
I'm saying.
right. Yeah. Yeah. No. Okay, so I understand the question. So we'll when we get to the final theorem, that sense will be made explicit. But it's what you would probably first guess if you had pen and paper.
Tom?
Yeah.
Does this proof rely on anything special about FD vect, or
No.
this is just general for any functor?
What, the initiality statement?
I mean this eventual image functor. You can prove this just with the properties of that.
Right. You're right. You can prove this. You can prove this. You can prove what's showing there with. That's just a very general statement. It's got almost nothing to do with vector spaces. That is perhaps not. I can't remember. Okay. So back to the invertible spectrum. I didn't entirely answer the question of why we should throw away the zero eigenvalue, but here, this is the slide where you already see it. So again, let's start with two linear maps in opposite directions. And a very similar argument to the one I just showed you says that not only are the eventual images isomorphic, but also the eventual eigenspaces are all isomorphic. All the non-zero eventual eigenspaces. So perhaps I should explain where the non-zeroness comes in here. So we have f and g restrictor maps back and forth like this. If you compose this, well, you get something that you can call GF, and of course it's a restriction of GF. But the point is that we know that that GF, well, we know that the only eigenvalue is lambda. So if lambda is non-zero, that means that its only where its only eigenvalue is non-zero, which means it's invertible. And that means, again, that the composites both ways, GF and FG are both invertible, and therefore F and G are both invertible. If lambda is 0, then that argument doesn't work at all, because it means that GF is not only, it badly fails to be invertible. Okay, so that's roughly the reason why this works. So anyway, so a similar argument tells you this, and this tells you that GF and FG have got the same non-zero eigenvalues with the same algebraic multiplicity exam. Maybe this is something you learnt in linear algebra in your first year at university, I don't know. But GF and FG for any two linear maps in opposite directions have the same algebraic multiplicities and in fact the same geometric multiplicities. Non-zero for non-zero eigenvalues. And another way of saying that is that the invertible spectrum is a cyclic invariant. On the other hand, it's just a fact of life. It's not something that's coming from my approach to anything whatsoever. That having an eigenvalue of 0 is not a cyclic invariant. So if you think about a one-dimensional vector space and a two-dimensional vector space and first inclusion and first projection, then the composite map from K to K is the identity, which doesn't have eigenvalue 0, and the composite map from K plus K to itself is certainly not invertible, so it does have eigenvalue 0. So, as I said, it's just a fact of life that 0 eigenvalues behave differently in this sense, and there's no getting away from it. So it's not a cyclic invariant. All the others are, but 0 isn't. Okay, so that's a natural point for questions on that if there are any. Okay, I'll move on. So the other word in the theorem that I had to explain was balanced, and this requires a little bit of thinking around. So I'll give you a couple of examples that have nothing to do with linear algebra. So I looked on Wikipedia last night. There's apparently an invariant of rings called left perfect. I don't actually know what the definition is, and it's better if you don't either. Maybe you do. But as soon as you know that left perfect is an invariant of rings, and as soon as you know it's an important invariant, you know there must also be a right perfect as well, and it must be equally important. And so if we're speaking formally, then the way to look at it is that given a ring, you can form an opposite ring, which you just do by reversing the order of multiplication, and then left ideals turn into right ideals, left perfect must turn into right perfect. And in informal terms, this is an automorphism of the category of rings. It's an invertible way of turning one ring into another that's functorial, and R being right perfect is equivalent to R op being left perfect. Okay? And then here's another example from the world of metric spaces. Sometimes people thinking about metric spaces, compact spaces, think about the number of balls that you need to cover, the minimum number of balls you need to cover the space. And you might start out by thinking about the number of balls of radius 1 that you need to cover the space. But as soon as someone's written that definition down and declared that it's an interesting thing to do, you know that it must be interesting to think about the number of balls of other radiuses that you need to cover the space. That's just kind of intuitively clear, right? But also it can be put formally again that if we write Tx for a space x scaled up by a factor of t, then this gives you a whole family, a one-parameter family of automorphisms of the category of vector spaces. Category of metric spaces, rather. And then the number of balls of radius r that you need to cover x is given in terms of n1, like this. So, in both cases, what you're doing is not only thinking about the invariant, in the first case, is it left perfect, that's a true-false invariant, and in the second case, number of balls you need. You're thinking about the invariant after you've applied an automorphism. So in this case, after you've applied the automorphism op, in that case, after you've applied the automorphism, the scaling automorphism. And so there's some kind of lesson there, that whenever you think about an invariant, you should also think about what happens after you've done an automorphism. I was teaching linear algebra to first-year students this year, as probably some of you were also doing, and I had to at some point motivate the concept of eigenvalue. And I really wanted to find a way of saying the following to them without the categorical overhead. So here's a third example from linear algebra. So we all agree that being invertible, whether you're invertible or singular, is an important question to ask of linear operators. Now we've got all these automorphisms of the category of operators, given by adding or subtracting a scalar multiple of the identity. So by the principle I just said, not only should you ask whether your operator is invertible, you should ask whether all its brothers and sisters are invertible. And so that must be important too, on principle. And of course, we know that it is, because that's exactly what it means to be an eigenvalue, and we all know that it's important, but this is one way of motivating the concept of eigenvalue. Okay, so that's all background to lead up to the following definition, and which is, I'm going to say that an invariant is balanced if it looks at an object from all directions, if it's not kind of tilted one way or another. And what I mean by that is that whenever you have an automorphism of your category, if your invariant takes equal values on two objects, then that's the same is true after you've applied your automorphism. So it's probably best illustrated by some examples, and by this paraphrase here that, loosely speaking, phi is balanced if knowing phi of E, but not E, tells you what phi of f of E is for any automorphism f. So if you just know whether a ring is left perfect, that's not a balanced invariant. It's just looking at the left-hand side, not the right. If you know whether it's left perfect and know whether it's right perfect, that is a balanced invariant. So notice I know nothing whatsoever about the logical implications between being left perfect and right perfect. And for all I know, it's not possible to be both, or one always implies the other, or whatever, I don't know. But whatever the situation is, this is always a balanced invariant. And the metric space example, just knowing how many balls of radius 1 you need to cover the space, that's not a balanced invariant. But if you know how many balls of all radiuses that you need to cover the space, that is a balanced invariant. So I guess it's a fact in the background here that these rescaling automorphisms are the only automorphisms of the category of metric spaces. And then the third example, the linear algebra one, just knowing whether your operator is injective is not a balanced invariant, because you're failing to apply automorphisms to it before applying the invariant. But knowing the set of all eigenvalues, that is a balanced invariant. So I think that's that for balanced invariants. Okay. So here's the most important example, that the spectrum and the invertible spectrum are both balanced. So we have these invariants, and these are invariants on the category of operators, which has some obvious automorphisms. You can take an affine function, so multiply by a scalar and then add on some scalar multiple of the identity, and as long as the scalar you multiply by this alpha here, as long as it's non-zero, this is an automorphism. It's a kind of basic fact about eigenvalues that this equation holds, which means that if you know the spectrum of t, then you know the spectrum of alpha t plus b. Now, I said this category has some obvious automorphisms, and it does, but it also has some non-obvious ones. And I don't think I'll say what they are, but there are some ones that are really quite tricky. So unexpected automorphisms are the category of finite-dimensional vector spaces. But even so, whatever automorphism you take, it's a fact that that knowing the spectrum of t determines the spectrum of f of t for all automorphisms f. These phi's should really be f's. And that means that, and the same is also true of the invertible spectrum. It's slightly less obvious, but it's also true that's the invertible spectrum. Which means that these things are balanced invariants of linear operators. They behave stably with respect to automorphisms in this sense. Okay. Right. So we get to the theorem. So here's the theorem, slightly rephrased from what I said at the beginning of the talk. That the invertible spectrum is the universal cyclic balanced invariant of linear operators on finite-dimensional vector spaces. So here's what that means explicitly. This answers your question, Samson. If we take any set omega and any invariant, so again this just means isomorphism classes of objects, isomorphism classes of linear operators, and it has the cyclicity property, this trace-like property, and it has this balance property. If those things happen, if it shares those properties with the invertible spectrum, then there's a unique thing you can do after the invertible spectrum to obtain phi. So a kind of crude way of saying this, well, it's not too crude. One way of saying this is that if you have any phi, any invariant phi satisfying 1 and 2, then it's a specialization of the invertible spectrum. It carries less information than the invertible spectrum. If you know the invertible spectrum, then you know phi. So that's what the theorem says. And I promised that there weren't really going to be any proofs in this talk, and I'm not going to prove this. But almost inevitably, the proof involves the Jordan normal form, and in fact, it's not too bad. Let me give one example of this, and it's not a very impressive example, but it's something. So trace is cyclic. Trace of GF is trace of FG, and trace is also balanced. If two operators have the same trace, then, for example, so let's think about the automorphism here that adds lambda. So you know that if the trace of T1 is equal to the trace of T2, then that implies that the trace of T1 plus lambda is equal to the trace of T2 plus lambda, because traces of sums are easy to handle. Okay, so for that kind of reason, trace is balanced as well as being cyclic. So, according to this theorem, it must be possible to obtain the trace from the invertible spectrum. Well, I mean, you knew that anyway, because the trace is the sum of the eigenvalues. There's just one little subtlety here. The trace is the sum with multiplicities of the eigenvalues. We only know the invertible spectrum, so we only have the multiplicities of the non-zero eigenvalues in front of us. But of course, it doesn't matter how many zeros you add. Okay. So that's that. I mean, you can ask what the point of that is, and one of the points is that you might want to do it in different categories. So there's no, this theorem here makes no reference whatsoever to the specific structure of vector spaces. You could ask in any category whatsoever for the universal cyclic balanced invariance of endomorphisms in it. And I've only really looked into one other case of this, which is finite sets. So we're going to replace the finite dimensional vector space by a different category, and so finite dimensional vector spaces are meant to be a little bit like finite sets, right? Finite dimensionality is meant to be like finiteness, and so the the endomorphisms of finite sets is very curious. It's another strange thing about undergraduate education that we spend, I mean, if you do a maths degree at least, you spend a vast amount of time thinking about automorphisms of finite sets, in other words, permutations, but almost no time thinking about non-invertible endomorphisms of finite sets. Anyway, they tend to look like this. What happens is you wander around for a while, and then eventually you get trapped in a cycle. There's no escape. And so a typical endomorphism looks something like this. And you can show that the universal cyclic balanced invariant of endomorphisms of finite sets is the thing that tells you how many cycles there are of each period. So it's an infinite sequence of natural numbers. So here, for instance, there's 1 5 cycle and 1 3 cycle. So this endomorphism here would get sent to, let's see, number of 1 cycles is 0, number of 2 cycles is 0, number of 3 cycles is 1, number of 4 cycles is 0, number of 5 cycles is 1, and then there are no others. Okay, so that's the analog of the spectrum, invertible spectrum for finite sets. Okay, so and it's you know, it's a sensible thing that you would probably want to know. It tells you about it tells you a lot about the underlying automorphism of this endomorphism. Okay, so I wasn't sure whether I was going to have time for this, but I think I do. How much time do I actually have?
10 minutes.
10 minutes, okay, good. So there's just a little postscript here, which is kind of inevitably directed to more to some parts of the audience than others. I mean, so much of mathematics is subsumed by the kind of Grothendieck era work on you know, galactic everything, and I think some of this is too, but I'm not really quite sure what I think about this, which is partly why I put it as a postscript. I said at the beginning that there's this notion of the spectrum of a commutative ring, and the fact is that in some sense it subsumes the notion of the spectrum of a linear operator. So here's the definition: the spectrum of a ring, I'll always mean commutative ring from now on. The spectrum of a ring is a set of prime ideals, but it's more than just a set. It also comes equipped with a certain topology, the Zariski topology, and a certain sheaf of local rings. And if you understand the spectrum of a ring to come equipped with this structure, then the spectrum of a linear operator is a special case in the following sense. Given an operator, you get a ring, namely the polynomial ring, factored out by the characteristic polynomial. And then you can take the spectrum of that ring. And the spectrum of that ring, well, the prime ideals are the ideals generated by these polynomials here, these m polynomials, where lambda 1 up to lambda m are the eigenvalues. So that means that merely as a set, spec R determines the eigenvalues. But moreover, if you use this extra structure, this sheaf of local rings, then the stalks of the sheaf of local rings have these dimensions, the dimensions of the algebraic multiplicities. So if you take this whole thing, the whole of spec RT, then that gives you the whole of spec T. So in that sense, the definition of the spectrum of a linear operator is swallowed up by the definition of the spectrum of a ring, and that means if you have a nice, clean characterization of the spectrum of a ring, then you can claim to have a nice characterization of the spectrum of an operator, and much else besides. And here there is a really beautiful theorem that tells you how to understand the spectrum of a ring abstractly. And so this is due to Hakim, this work from the early 70s, and I think deserves to be better known. among category theorists than it is well, among everyone, but in particular among category theorists. And the way I like to think about it is as follows. There are rings, and then there are these special kinds of rings called local rings, and there's an inclusion factor. And it completely fails to have an adjoint. It just doesn't, and you wouldn't expect it to. And you could just give up, but you don't give up. And you make a very bold move, which is to say, well, it doesn't have an adjoint if you're talking about rings in the topos of sets, or local rings in the topos of sets, but maybe I'll let my ambient topos vary. And so let's write ring topos for the category of topos is equipped with a ring inside it. Right, so an object of this category is a topos E together with a ring in E, and I didn't write it, but a map in this category is a geometric morphism together with the kind of thing that you would probably guess if you have any idea what I'm talking about at all. And then similarly, there's a category of topos is equipped with a local ring. And it's a fact that this inclusion functor does have an adjoint, a right adjoint. So although this one of local rings in set into rings in set doesn't, this one does. And moreover, if you think about it, if you know the story of classifying toposes, the reason why this has a right adjoint is actually it's completely general. It's got nothing particularly to do with the theory of rings or the theory of local rings. It's almost trivial. And so you can think of this adjoint as something like constructing the free local ring on a ring, but that's with it understood that you might end up in a different topos than the one you started with, that you don't have the right to stay in the topos that you want to stay in. Okay, so what's this got to do with Spectra or anything? Well, the spectrum is somehow that free local ring. So let's just go through this. If we start out with an ordinary ring, that's a ring in set. And so you can think of it as an object of this category here. It's the topos of sets together with a ring object in it. On the other hand, we've got a topological space, and if we think topos-theoretically, then that means we've got a topos, the topos of sheaves on it. And the sheaf of local rings on it is then best regarded as a local ring in that topos. So what that means is that spec R can be thought of as a, so say, locally rings topos, a topos equipped with a local ring inside it. And what Hakim proved is that this right adjoint to the inclusion, this free local ring functor, is exactly the spectrum construction. So if you start out with a ring, an ordinary ring, then you get the spectrum with a sheaf of local rings. That's exactly what it does. And so spec is described as a right adjoint. So it's a beautiful description of the spectrum of a commutative ring as an adjoint functor. And moreover, this tells you how to define the spectrum of a ring in any other topos, not just in the category sense. So that seems like it's kind of, effortlessly superior to everything I've said, and maybe it is. Because it describes the universal property of the spectrum of a ring, the spectrum of a linear operator is a special case, and so it gives you this abstract description of the spectrum of an operator. However, I just have two reservations about it. And the first one is that when I showed you how to see the spectrum of an operator as a special case of the spectrum of a ring, we had to use the characteristic polynomial. And that was just kind of written down explicitly. It's less clear where the characteristic polynomial comes from, what its place is in an abstract description.
You only mod it out by the characteristic polynomial. Isn't that the same as just the ring of all the powers of T?
No, because that would be the minimal polynomial. So that's what people usually. Usually, when people associate a ring to an operator, they mod out by the minimal polynomial effectively. So they see what they declare two polynomials in T to be equivalent if they have the same effect on the space. That's what you meant, yeah. And if you use the minimal polynomial, you wouldn't get the algebraic multiplicities. You get the I don't know what they're called, the powers in the middle polynomial. So there's that. And the other thing is that it's simply a different characterization. I mean, it's often useful, sometimes things have many universal properties or many characterizations, and it's useful to have many of them. So it's just something different. And the one that I presented to you stays in the topos of sets, which hadn't occurred to me that might be a virtue until I saw Hakim's theorem, but it's somewhat more direct in that sense. So that's all I had to say. Thank you very much for listening.
Questions? Comments? Yeah.
Do you say something about the weird automorphisms of the canopy vector spaces and Y trace respect to them?
Right. So there's two questions. I'll answer the second one first. So why trace or invertible spectrum? In order to show that they respect all of the automorphisms, you don't need to know anything about what the automorphisms are. You don't need to classify them all. You can just prove generally that it happens. So, okay. So the point is, I guess, that if you take any operator, then it decomposes in this way. And you can apply different automorphisms on different summands. So if you put it in terms of Jordan normal form, you can do funny things like this. So here's a matrix in Jordan normal form with 2 2s and 3 3s. I can multiply the top block by 3 over 2 and the bottom block by 2 over 3. So I'll get 3 over 2, 3, 2, 2, 2, 2 over 3, 2 over 3. So anytime you have a permutation of the scalar field that leaves 0 fixed, you can do something like this. And I think there are other ones as well.
Are there any valid cyclic invariants at all if one is looking at the category of endomorphisms of an infinite dimensional vector space?
I don't know any. I don't know the answer. That's a good question.
Chris has another question.
Maybe a question for you mentioned in the beginning some crazy people might look for a spectrum of non-commutative things.
Yeah.
What would you
I had
say
you in mind.
a candidate has to satisfy to deserve the name spectrum?
I don't know. I mean, I'm well aware that this result here is very much tied to the finite world. For example, if you try and do it in say Banach spaces, then it just all goes wrong as soon as you have any kind of infinite dimensionality. And so I don't really feel confident that this is the right way to look at it, to be perfectly frank. So I don't feel qualified to answer your question.
I have a sort of dumb question that
Yeah.
relates to the sort of initial teaching motivation you were mentioning. So this is a very elegant point of view of this whole point of view on doing linear algebra. How far away are we from the algorithmic perspective? I mean, is it in there at a small remove? I mean, in this kind of...
When you said it, the algorithmic,
Well,
perspective.
actually using, computing things. And,
how do you compute the eigenvalues of a 2x2 matrix?
Yeah.
Yeah, I mean, this is a question that, you can actually push this approach to do that kind of computation, although Axler doesn't really. So some people's response to that question, some people would defend Axler by saying, well, everyone who ever takes a linear algebra course is completely deceived because the way we all learn of computing eigenvalues, it certainly doesn't work above 5 by 5, above 4x4 even, and then it's kind of impractical for even 4x4 probably. So, you know, if you're looking for numerical solutions, then you use completely different algorithms. But maybe that's not what you're asking.
I don't know. I'm not sure.
Yeah.
Okay. But you don't think there is a nice connection? I mean, by using iterative methods.
I don't know. I mean, I suppose you could look at what I said with the definition of trace and determinant characteristic polynomial and so on as just kind of a rearrangement of the beginning of